Now what are these 17 two-dimensional plane groups? Only 17 different ways in which a periodic pattern in 2 dimensions can have its symmetry. So, a periodic pattern, any periodic pattern, whether it is a floor tiling or a textile pattern or a 2-dimensional crystal like graphene. So, graphene has to be one of these point groups. You know it is 6-fold. So, it has to be either 6 or 6 mm. So, all these 2-dimensional patterns can have only 17 different types. So, 17 different ways is in 2D, that is the 17 plane groups, or also known sometimes more colorfully known as 17 wallpaper groups. So, wallpapers can come in variety of attractive patterns, because those differences are coming from the difference in the motif, but when you look at the symmetry you have to fix them into one of these 17 types which have been derived. So, the first plane group is P1. P1, the first letter P gives that the unit cell is primitive, and the second number, that 1, gives that it has only one fold axis. It does not even have a two-fold symmetry. Now, you know that if you have a lattice, it is going to have a two-fold symmetry. So, the only way you can destroy that two-fold or avoid having two-fold is by putting something at the lattice point which does not have two-fold and is not consistent with this two-fold. Okay. So, suppose these are all only lattice points. Now, suppose let us try to make a pattern, some very simple pattern. So, and so let me select an object which has no two-fold. So, maybe let me select a letter P which has no two-fold, no mirror plane. So, it is an asymmetric object. So, since I put that at one lattice point, I will put them at each lattice point. As soon as I put at each lattice point, you can see that the beautiful two-fold symmetry of the lattice point, the original lattice point, the oblique lattice point, which was having this two-fold symmetry, because every lattice point had a correspondingly negative lattice point. But now, because of placing this P, that beauty or that symmetry is lost, because for this to be now a two-fold, if we want this to be a two-fold, this P has to be rotated by 180 degree, and there should have been another 180 degree rotated P there. Only if I have that, then this lattice point will now be a two-fold. So, you can see how the motif of the pattern is interacting with the symmetry of the lattice. Lattice as such had a two-fold, but as soon as I place this asymmetric motif, that two-fold is disturbed. So, and this is how you will generate a pattern with only one fold symmetry, because as we saw that in lattice we cannot have just one fold axis, but pattern can have, and this is an example of a plane group 1. The way I am drawing is what is also the convention in international table, that the axis A, the origin is always taken on the top left, origin is taken on the top left, the axis A is allowed to go down from there, axis B is taken to be horizontally going to the right. These are the drawing conventions. Of course, whichever way you draw, you will get a two dimensional lattice. I could have taken my A this way and B this way, or A that way and B that way. However, this is an accepted convention because I want to teach you international tables also, and we should means, and that is a convention which is followed by the international community of crystallographers. So, it is important to remember that and follow those conventions. So, this choosing the origin on the top left and letting A come down and B go right, these are accepted conventions as per the international tables. Now, within oblique lattice, I can have the next plane group P2. Now, by P again you are reminded that it is primitive, and by 2 you are told that it is going, the pattern has twofold. Since the pattern has twofold, so you have to select a proper motif to preserve the twofold of the original lattice. Lattice anyway had twofold, but now I want that twofold in my pattern also. So, I will, as I told you, if I place a P, I should place an equivalent P or a rotated P about the twofold axis. So, the way to do that, again in international tables, they do not select P or something, they just select a circle, and to give you a twofold, they will put another circle which is related to the original circle by 180 degree rotation about the lattice point. Of course, by translation you will generate similar pair about each lattice point. Each lattice point has to have identical neighbors. So, now you have this two circle motif giving you a twofold at each lattice point, which is repeating. I just removed it because again following international tables, I should draw the symmetry elements in a different unit cell. So, the international table page will give you two different drawings, one just for the symmetry elements. So, these are the two folds which you will have in this pattern. So, you could have shown it here, that is what I was trying to do in beforehand, but you can do it in a separate pattern also. So, this is called, the first diagram will be called a general Pigesen diagram, and the second one will be called symmetry element diagram. It is called general Pigesen because see, deliberately I have selected my circle in a general position. What is general about it? Only one kind of special positions are there in this, means all the special positions are the positions where some symmetry element is there. So, if I put my circle on a twofold, since I did not put my here there was a twofold, here there was a twofold, and since I put a circle here, the twofold generated another circle here. But suppose I put a circle on the twofold itself, means what the twofold will generate. it will rotate that circle there itself by 180 degree. So, it will not generate a new circle. So, these points which are on the symmetry axis have lesser number of equivalent points than a general position. How many equivalent points are there within the unit cell? How many equivalent general positions are there within the unit cell? Just two. You can see that only two of them are lying inside, isn't it? 1 and 2. So, if we were actually strictly drawing only the contents of a unit cell, only these 1 and 2 we should have drawn. That should be sufficient to give you all the positions by translations. So, there are two general positions within the unit cell, but if the point was lying on the lattice point, then you would have got only one, because if I if I repeat this green one will come only at the corners, and you know anything sitting at the corner in terms of equivalent counting for the entire unit cell, it will come out to be 1, because each corner is shared by 4 unit cell. So, let us look at how this information is given in the international table. So, this is the page of an international table, the P1 group which we discussed, P1. So, every space group or every plane group is given a number. This is for a ready reference, a serial number. This is a sort of a serial number. Serial number of international table. This has no scientific content. This is just they have arranged it. So, 1 is not 1 fold or 2 fold or anything, because it will keep going from 1 to 17. So, the first one without any symmetry, they have called it number 1. P1 is the international symbol for the plane group. 1 is the point group. Oblique is the lattice type. This is called a short symbol. The first one in bold is called the short symbol. This is called a full symbol. In this case, the full symbol and short symbol are the same. So, effectively there is no short symbol, because it is already so short, you can't reduce it any further. So, P1 full symbol and short symbol are the same. Patterson symmetry is something which we will not discuss. So, we are not keeping that in the current discussion, but there is an information. This has to deal with the diffraction patterns. Now, let us look at one by one the other items. Origin is arbitrary, and the two diagrams. So, this was the symmetry diagram. I drew it in the reverse way. So, I did not follow the international style. I first saw the general position on the left and symmetry on the right, but you are seeing that international table actually shows symmetry on the right and the general position on the left. So, this is a single unit cell. The two lines in between drawn here are only reference lines, just to divide the unit cell into 4 quarters. So, these are neither mirror plane, or these lines are just reference lines. Asymmetric unit. Now, unit cell itself is a unit. The very name unit justifies that it is a unit. but it is a unit by translation, that if you translate this unit you will generate the entire lattice. So, you have to translate it next to each other, then you will fill the space. So, that is translation. However, if there are rotations, reflections, then you can generate new motif by rotation or reflection also. If you are able to do that, then you can select a part even smaller than the unit cell. We will see that in P2, in P1 it is not there, we will see in P2. You can select a part smaller than the unit cell which can repeat by the rotational or reflection symmetry and generate the entire pattern. If you are able to do that, that is called the asymmetric unit. The smallest part of a pattern that can generate the entire pattern by application of rotation and reflection, not translation. The smallest part of the pattern which can generate the entire pattern by translation is the unit cell, the primitive unit cell. But the smallest part of a pattern that can generate the entire pattern by application of rotation and reflection is known as the asymmetric unit. Then we have symmetry operation, and again there may be many symmetry operations, so they are numbered. So, the first item 1 here is the number of the symmetry operation. So, if there were 10 symmetry operations, they will be numbered 1, 2, 3, 4. Here there is only one symmetry, because we have decided that this is a plane group with lowest symmetry, this is a plane group with point group 1. So, only one fold rotation symmetry is there. So, there is no two fold, no three fold, no mirror planes, no nothing. So, that means there is only one symmetry operation, and that is the one fold axis. So, that is listed there. Generators selected. Now, every group has generators. By generator we mean a small, not necessarily smallest. A small subset of a group element, small subset of a group I can say, which can generate all other elements by group multiplications. The group 4, you know, group 4 is consisting of 1, 4 plus, 2 and 4 minus. It is a group of order 4, 4 elements are there. However, I can select 4 plus as my generator. How? I know 4 plus is 4 plus, and since my generator is only 4 plus, I can combine 4 plus with itself. So, 4 plus into 4 plus, 4 plus is square, that is 2, 90, 180 degree rotation. 4 plus cube is 4 minus, and 4 plus 4, 360 degree rotation, which is identity. So, all the operations of the group can be generated by only one element, and that element is a generator. Okay. But selection of generator is not unique. So, can you select another generator for this? 4 minus. Can you select 2 as generator? No. So, it is not that any arbitrary element is a generator. So, you have to choose your generator carefully, because 2 will never get 4. So, if you can find a single generator for a group, it is not possible for all the groups, we will see. So, in this case it is possible that by a single generator you are able to find, that means you can describe the entire group. So, that is the definition of a cyclic group. So, 4 is a cyclic group, but suppose you had a group, let us say a group which is not cyclic. So, 2 mm, one simple group which is not cyclic is 2 mm. So, this is also a group of order 4. What are the members of this group? 1, 2, let us call mx and my, 2 perpendicular mirrors. Now, you can see 1 obviously cannot generate any group. So, 1 is not a generator. 2 square will give 1, and a type 1 operator can never generate type 2 operator by its own multiplication. So, I can never get mx and my from 2. If I select mx, product of 2 mirrors will always be a type 1. So, it will either be rotation 1 or 2. So, again it cannot generate. So, individually none of them can generate. You can see mx square is also 1. Just because square itself is 1, after that any power will repeat itself or 1, because they are self inverses. So, no single element can generate, not a cyclic group. These are for finite groups. For translations also, translations are infinite group. So, when you say that A and B are your lattice translations, so these translations themselves are operators, because they move each point from one place to other place. Just like rotation moves one point to another point, reflection moves one point to another point, translation also moves one point to another point. So, translations can also be seen as operators or group operations, and you can make your group translation group so that will consist of all the translations of the lattice. Now, what are all the translations of the lattice? So, any integer times a plus another integer times b is the translations of the lattice. But integers are infinite and you have 2 integers here to play with. So, both m and n will go minus infinity to plus infinity. So, there are infinitely many translations in this group. So, this is an example of an infinite group. But although infinite, you can see that this group is generated by only 2 translations A and B, because all other translations are combinations of these 2 translations. So, A and B generator of the infinite translation group. Let us go back now to international table to understand generators selected. 1 just gives you the number of symmetry, means number of the symmetry operation which is selected, and so you have to go back to understand this one is this one. So, means one fold axis. Now, it is really silly to select one fold axis as a generator, because one fold does not give anything. With itself it will keep giving 1, with any other operator it will keep repeating that operator for some reason this 1 is always means identity operator is always selected as an generator, part of the generator. So, it is trivial, but it is kept there for some reason not very clear to me. So, we will accept that 1 is there as the generator. What are the generator? It has no other symmetry operation in terms of rotation and reflection, but translations are required to generate the full group, because we are now talking of plane group, that is the 2 dimensional space group. So, 2 translations, translation 1 0 and translation 0 1. Remember 1 0 and 0 1 is in the crystallographic notation now, they are not orthogonal unit vectors. 1 0 is nothing but A, and 0 1 is nothing but B. So, these two vectors if you combine you will get. So, these three generators have been selected, one is trivial, two of them are required T 10 and T 01, and T 10 and 01 combined will give you the entire pattern of lattice. So, generators selected. Now comes the general position, and there is a technical jargon here, Wyckoff letter, multiplicity, site symmetry. So, there are three things actually. So, actually it is written in the same sequence in which these numbers are coming. So, multiplicity is 1, Wyckoff letter is A, and the site symmetry is 1, and this one just gives you again how many, means all the different positions. So, there is only one position, there is only one general position. Let us go back here. In the unit cell there is only one equivalent position, because this is P 1. So, neither rotation nor reflection. By translation you will generate the new one, but by translation the new one which you will generate always will go out of the unit cell. So, the B translation takes you out on that side, the A translation takes you out on this side. So, they are not lying in the unit cell. So, the total number of equivalent position which is there within the unit cell, that is what is known as the multiplicity, and that is 1.
Example, you said 2 equivalent positions. I mean, were they equivalent?
Yeah, because there were two folds. So, two-fold was made equivalent by not only by translation, but by any other symmetry. So, total number of positions. So, symmetry equivalent, whatever may be the symmetry, rotation symmetry, reflection symmetry, translation symmetry. So, in this case it is nice, means this is a very boring point group, it is a very boring plane group, it has no symmetry. So, but it is nice, it for the same reason it is very simple also, it does not have much to show, and since it does not have much to show, it is simpler, and many of the things are coming as trivial here, but we will look at them in more detail there. So, this A again is an arbitrary numbering or arbitrary letter, it always starts with A for the most symmetric position. Most symmetric position is given the designation A, and now since this is such a simple space group, since it has no other rotation, reflection or anything, whatever position you select in this unit cell, you can, means you may disagree or you may dislike my green circle and you will say that I'll select a point right in the center there or something. However, right in the center there also is in no way more special than this green one. Only the xy coordinates have changed. Right in the center is half half, but that half half, although for this particular unit cell you can say is a special, but from symmetry point of view it is no more special. The green also had no symmetry, it was not sitting on a mirror plane, it was not sitting on a rotation axis. The red is also not sitting on a mirror plane, not sitting on a rotation axis. So, in terms of their qualification to be called a special points, they are equally disqualified. So, both of them are general position, and so the most symmetric position itself has no symmetry, that is what is given as the site symmetry, that what is the symmetry at that site. So, symmetry at that site is no symmetry, because nowhere in this plane group there is any symmetry other than translations. So, no position, any arbitrary position x y, all will have only one fold rotation axis passing through them. So, the site symmetry will always be 1. So, only one kind of position designated as Wyckoff. So, Wyckoff was a crystallographer who developed this notation. So, that is where the name Wyckoff comes, and that is, so we will say, so any point we choose here, we will say that that is at site A, Wyckoff type A. Now, this makes no sense here because there is only Wyckoff type A, but in other systems you will see, more symmetric systems, you will start having more types. Then it makes sense to say that whether the atom is located at type A, Wyckoff letter A, or Wyckoff letter B, site A or site B. So, let us do that, because we will not currently, if time permits, we will look at this. And this is an older version of international table. In the most latest version, this has disappeared, maximal and non-maximal isomorphic subgroup. In volume, there are several volumes. So, this is the volume A we are discussing, volume A. So, this is an older volume A which has this information. Newer edition you will not find it in volume A. Newer edition, this information is shifted to volume E. So, we will take that shortcut by saying that we are discussing volume A of the newer edition. So, we will not be discussing this particular aspect at the moment. On the right hand side also you see there are some reflection conditions. So, those who are interested in diffraction, so you have to worry about this also. But looking at the structure in a purely geometrical way, if you are not connecting it with diffraction, then these reflection conditions also are of not importance. Now comes the point with the plane group P2. Again the lattice is oblique. Now the point group, I told you that this middle symbol is the point group. Yeah. So, point group 2, now the left hand figure makes little bit more sense and is more attractive, because it has now the two folds distributed everywhere, not everywhere, but on the corners, on the middle of edges, and in the middle of the cell. There are so many two folds, and that comes from our combination principle. We know that between any two lattice translations, the midpoint will always be also a two-fold. If the lattice points have two-fold, so if the corners are two-fold, then half the lattice translations along the edges gets two-fold, half the lattice translation along the diagonal gets the central two-fold. So, two folds will come. Now, you can see that if I take this as my general position, the red circle, then the central two-fold, which is not shown in this diagram, but is shown on the left hand diagram, will make this two-fold replicate this motif there. So, both these motifs are now equivalent with respect to the symmetry, although they are not translationally equivalent. Okay. They are not translationally equivalent, but they are still symmetry equivalent, equivalent by central two-fold. Okay. So, you can now see that Wyckoff positions now take nice meaningful 5 values A, B, C, D, E, so many different Wyckoff positions with different multiplicity and different site symmetry and different coordinates. Also, you see the symmetry operation now becomes non-trivial. One fold will of course be there, that is the unit or the 0 of symmetry, which is there in or is always there, but now you have the second symmetry operation, which is a two-fold. So, this bracket 2 is just the number, second symmetry operation. The next 2 is two-fold, and 0 0 is position. So, the two-fold is at the origin. So, this two-fold is considered as the two symmetry operations. Generators, again the trivial generator, the identity, two translations you require anyway, as well as neither the translation nor the identity can give you the two-fold of the pattern. So, you require the two-fold also. So, it is not saying this 2 is not saying two-fold, this 2 is saying the second operation in the second item in the list of symmetry operations. In this case, it happens that that is also a two-fold, but you should not take this number 2 if it is written 3 that it is a three-fold. That need not be the case. You have to go back and look at the symmetry operation. So, look at the second item in the symmetry operation, that is a two-fold. So, that is what is selected as generator. Now, I told you that A is always selected as the most symmetric location. What is the most symmetric location? On the two-fold. Okay. So, and if I selected my green circle on the two-fold, then this central two-fold will also repeat it here on the corner only. Now, I will get only at the corners. So, whatever I put at site A will have only one member, one representative member, one equivalent symmetry equivalent member. So, if my green circle is at 0 0, that is the position, that is the Wyckoff site A. So, it has multiplicity only 1, because within the unit cell there is only one equivalent. So, that is why the multiplicity 1, Wyckoff designation A given arbitrarily by Professor Wyckoff, and 2 is its site symmetry. So, what is the symmetry at the location A? It is on the two-fold. So, that is the site symmetry. B, C and D you see are other two folds in the pattern. So, at 0 half, 0 half is also a two-fold, half 0 is also a two-fold, and half half is also a two-fold. So, again arbitrarily 0 half, half 0 and half half given B, C and D. Finally comes E, the least symmetric, which is my red point here, because it is not on any symmetry axis. So, that becomes E. Now, the multiplicity becomes 2, because anything which is not on the symmetry axis will replicate twice by the symmetry operation within the unit cell. So, that is the justification for 2, but now what is the site symmetry? No symmetry. So, that is one fold, and these coordinate gives you that if you start with any coordinate x y, what will be other coordinates which you will generate. So, if you start with x y, you will also generate x bar y bar because of the two-fold at the origin. So, if this is x y, this is x bar y bar. So, although it says multiplicity 2, how many equivalent points are within the unit cell, it is not giving you the coordinate of this and this, it could have given you the coordinates of this and this, but it tries to relate the nearby one because it is much easier to see and much easier to give the coordinates. So, x y is related to x bar y bar, which is outside the unit cell, rather than this one which is inside the unit cell. Okay. So, thank you very much.